This week we are covering two sections. We are covering 4.2 to talk about mins and maxes, and 4.3 derivatives, shapes of curves. So recall back when we were in front of each other on campus, I mentioned that we were guesstimating what the curves looked like. All we knew how to draw a derivative graph or original function was using the relationships between the first and the second derivative and the original function. Um, so let's recall a little bit about that before we dive into our section. All right, so whiteboard. So if you recall, if the first derivative is positive, bigger than zero, positive number, then the original function f of x was increasing. Again, sorry for how messy my handwriting is going to be. I'm making do with my iPad here. Okay, so we're increasing if the derivative is positive. If our first derivative is negative, then the original function was decreasing. Okay, that was one thing that we learned right before we started going online. We also introduced the second derivative and some properties. If the second derivative was positive, then recall the original function was known to be concave up, also known as a smile. And if the second derivative was negative, then we knew the original function was concave down. Oh, concave down, which if you recall is like a frowny face. Okay, let's jump to the PowerPoint. Talking about mins and maxes. So let C be a number in the domain of the function, which recall the domain is the x values. Then the y value, f of C, is the absolute maximum if there are no other values higher, and C, f of C, can be an absolute minimum as long as there are no other y values that are lower or smaller. So an absolute maximum or minimum sometimes is called a global max and min, and the max and min values of f are called extreme values. So if we look at this picture, I can see at B, so if you look at the x-axis at B, we have a local max. It's not a global max because it's not the ultimate top highest value. We see here at D, that is a global maximum. This is a local maximum. In this local little area here, we have a highest point. And we can see that there's a local min, but it's not global because we have points that are lower than that point. I really can't tell in this picture, but it doesn't look like this is a global min either. It looks like this is going to continue straight down, so there won't be a global min, and this is going to go straight up. So technically this shouldn't be a global max either, because this is indicated almost like an arrow at the end is going to keep going. But we do have global maxes. So two global maxes, sorry, not global, local, my apologies. Two local maxes and two local mins. Okay, so if we are defining this, this is what it would look like written in math language, defining local mins and max. It just means that in the remote area, it is the highest point or lowest point. Okay, so we have a graph that's labeled. These ends are assumed to keep going. So that means that this is a local and an absolute or global min because there is no value lower than those. This one's only a local min because this value is lower than that value. And this is a local max because the two ends continue to go up, so it is not the absolute highest point. So the first derivative test is what we will do in order to determine local mins and maxes and global mins and maxes. And the first step would be take the derivative of the function, sorry. The second step is to set the derivative equal to 0. Okay, because recall a derivative is the slope of the tangent line. If the slope of the tangent line is 0, it creates a horizontal line, okay, which identifies mins and maxes because all mins and maxes have tangent lines that are horizontal lines. Okay, we then solve for x when we set the derivative equal to 0 in order to find what's called critical values. Okay, these critical values are the points at which something's happening, whether it's a min or a max, or an inflection point. So if you recall, I introduced a reflection point recently as the point at which the smile turns upside down. So the smile turns into a frown or the frown turns into a smile. So it's the halfway point between the change in concavity. Okay. And then you have to do test points in order to determine what the critical value is. And we'll show you that in this example. So our example is using a function. Okay, so f of x or y equals x cubed minus 3x squared minus 9x. Let's jump over to the whiteboard. Okay, so we're using a function y equals x cubed minus 3x squared minus 9x. And step one is to find the derivative. So y prime, okay, we follow our power rule. So we're going to bring the 3 down in front and subtract 1. So we get 3x squared as the derivative of the first term, negative 6x as the derivative of the second term, and negative 9 the third. Then it tells us in step 2 to set the derivative equal to 0. So we set it equal to 0 because we want to find when is the derivative a slope of 0, indicating a min or a max. And it tells us to solve for x at this point. So I notice that all my coefficients are divisible by 3. It will make my life easier to factor out a 3. So I'm going to do that now. So I have a 3 out here, which gives me x squared minus 2x minus 3. Now this is an easier polynomial to factor because there's a positive 1 as the coefficient of x squared, which means we can factor by asking ourselves, oh, this 3 would be still out in front though. There we go. We just ask ourselves what two numbers multiply to negative 3 and add to negative 2. So we have negative 3 and positive 1. We have negative 3 times positive 1 or positive 3 times negative 1 are our only two options for our prime number of 3. So now we just have to figure out which one adds to the middle, and we want a negative number, so this is our combination. So we have x minus 3, x plus 1, our factored form. Now we need to use the zero product property. So the zero product property states that if two things are being multiplied and they equal 0, then one of these pieces had to be 0 to start with, or both. So we will find by saying, okay, 3 is equal to 0. That was the first part. Let's actually rewrite what we ended with. We ended with 0 is equal to 3 times x minus 3 times x plus 1. Now, zero product property says one of these three things has to be 0 in order to multiply to get 0. Well, we know that 3 is not the 0. That doesn't make sense. 0 does not equal 3. So that's out. That's something we don't even have to look at. But when is x minus 3 equal to 0? And when is x plus 1 equal to 0? So if I add 3 to both sides, I get x is equal to 3. This is one critical value. This is one of the critical values. The other critical value is going to be what we get over here. Okay, so we subtract 1 on both sides and we get x equals negative 1. So we have two critical values, x equals 3 and x equals negative 1. And what we know is that something's happening at these values. Either we have a max, a local or an absolute, a min, local or absolute, or it's possible it's just an inflection point. So it's just a change in concavity. And the only way to figure this out is to take a look at what's happening with the function. So let's write down what we have. We have critical values x equals 3 and x equals -1. Now, if we take a look, if we're looking at some function, I don't know if this is the graph of the function we're working with. I just drew a random graph, but I wanted to make it clear what we're really looking at here. Oh, I didn't do one with an inflection. Okay, hold on. Let me draw a new graph. Need it to have an inflection point too. So here we go. All right. So now if I'm looking at this graph, I would have a slope of 0 here. So we would identify this point as a critical value, whatever that would be. We would also find here that there is I didn't draw a very good inflection point. Okay, so let me draw a different curve for the inflection point one. But we can see that if we needed, if we found that the slope is equal to 0, then we know that something's there. If we're looking at, hold on, erase all this. Yeah. If we were looking at, let's say, this function, then again, we would find 3 critical values because at these 3 points, we would have a slope of 0. And in order to figure out if the critical point is a max or a min, we would be looking at what's happening before and after the point. So notice that this is increasing, okay, and this is decreasing. So recall what we did in the beginning of this video. Increasing function means that the derivative was positive, and decreasing function means that the derivative is negative. So what we're going to be doing is taking a test point before the point, a test point after, and plugging it into the derivative function, because we are going to try to find out whether before the point is it positive or negative, indicating increasing or decreasing, and after, same thing. Okay, if it's an inflection point, I'll show you what it looks like. So on a graph that has an inflection point, let's see. So we look at the standard normal curve, if any of you guys have history with statistics. The frown is turning upside down about here, about halfway. So we have 2 inflection points. We have a point here that would actually give us a slope of 0, or technically it's, yeah, it would be a slope of 0. And same here, that would give us a slope of 0, although it looks like that would be the tangent line, but inflection points have tangent lines of zeros as well. And what we would notice when we do our first derivative test to properly identify that this was a slope, to properly identify this is an inflection point and not a min or a max, there would be a critical point here too, by the way, is that when we check before the critical point, we'd see that we are increasing, indicating we would have found that the derivative was positive. And after, we still have an increase. So we'd still have the derivative being positive. So we'd have positive, positive, and that would say, oh, this critical value is an inflection point. It is not a min or a max. Because if we take a look at the min and maxes again, before and after, here's a max. Clearly, if we check the function prior, it'd be increasing. The derivative would have proven to be positive. And if we check the function after, we're decreasing. The derivative would have come out to be negative. So positive and then negative shows, oh, we have ourselves a high peak. It is a max. We're talking about a minimum, we would have negative decreasing to positive increasing. Okay, so now that we've taken a look at all the visuals, let's jump back to our example of what we were working with. And we found in our example that we have critical values of x equals 3 and x equals -1. So if we're looking at a number line, okay, -1 comes here. This is one critical value. And 3 is here. This is the second critical value. And what we want to do is pick test points in between. So a number less than -1, a number between -1 and 3, and and a number greater than 3. So let's pick -2 as a test point. Okay. And let's pick 0 as a test point because that's always an easy number to calculate with. And let's pick 4. Okay, it doesn't matter what you pick as long as they actually exist in the number line between the areas that we're using. You can't use -1 and 3 because when we put those into the derivative, we are just going to get 0. We already know that. That's why they are critical values. So we need to test -2, 0, and 4 in our derivative function. So let's do that now. Okay, so recall that our derivative was 3x squared minus 6x minus 9, and we are testing these three test points. So we have the derivative tested at -2 is what we're doing first. So if we test the derivative at -2, it means put -2 in for x and see if the answer is positive or negative. So we don't really care what the number is, we just care what the sign is on the answer. So -2 squared is going to be positive, and that's going to be a positive 4. We have 3 times positive 4. We have a negative times a negative, that gives us a positive. All right, we just have to make sure that the positive here is bigger than the -9. So we have 12 plus 12, which gives us 24 minus 9. Who cares what the number is? What we care about is it's positive. So we would mark between negative, on the left side of the critical value -1 would be positive, indicating increasing. And I'll draw this out after when we finish all of these calculations. So let me clear out. Oh, you know what? I should have just save myself the writing. Okay, let me clear out just what I inputted in here. I need to put my 3 back. Do that. All right, I'm just going to erase this stuff. Okay, there was a 3 here, and there was a prime here. Okay, so now we want to test the other test point. Our next test point is 0. So we'll put zeros in here. And again, we're looking to see if we're positive or negative. So we have 0 minus 9. This one's definitely negative. So we will indicate that between -1 and 3 is a decreasing portion of the function. All right, so now let's calculate the derivative at our last test point, which is 4. So we put 4 in, positive 4 in for every x, and we calculate. You could just put this in your calculator, but it's fairly simple to do out, so I'll do it with you. So we have 3 times 16, which is a big positive number, minus 24 minus 9. So we just have to make sure that 3 times 16 is a bigger number than -24 and -9 combined. So we have 3 times 16, which gives us 48. And we have a subtraction of 24. So 48 minus 24 is 24. And then we minus 9. And we're still going to have a positive result. It's going to be 15, but who cares? We just care that it's positive. So what it's saying is after a critical value of 3, we're expecting the function to increase again. So let me draw out what we just found. We had 2 critical values, a critical value of -1 and a critical value of 3. We chose 3 test points, -2, 0, and 4, in order to determine whether the function was increasing or decreasing around these critical values. we found that when we put -2 into the derivative, we had a positive result, which indicates an increasing function. When we put 0 into the derivative, we had a negative result, indicating a decreasing portion of the function. And when we put 4 into the derivative, we had a positive result, indicating increasing. So now we can see that the function looks like this, where our critical values are here and here. And we can also see what these critical values are. -1 is a max, while 3 is a min. And we know by the fact that it's a cubic function that these ends continue to go up to infinity, also continue to go down to infinity, which would mean that these are local maximums, not global. Okay, let's do one more example of the first derivative test. So the next example says use the first derivative test to find all the max and mins of the function y equals parentheses x squared minus 1 all raised to the third power cubed. So let's go to our whiteboard. First, step 1 is to find the derivative. So we're working with the function y equals x squared minus 1 all raised to the third power. This is the time where I'd ask you which one of our derivative rules should we use, and you guys would tell me that we are using the chain rule. So we're going to bring the 3 down in front. We are not touching the inside function. Come back up, subtract 1, and multiply by the derivative of what's inside, which is 2x. Okay, if we neaten this up a little bit so that when we have to work with it, solve for x, if we combine these are both being multiplied, then we have the derivative is equal to 6x times x squared minus 1. Step 2 is to take this derivative and, that's right, set it equal to 0 to solve for x and find all of the critical values. So we have our derivative is 6x times x squared minus 1 squared. We set it equal to 0. We already have a product. It's already factored, so we can set each piece of the product equal to 0 separately. So we get 6x is equal to 0, and we have x squared minus 1 squared is equal to 0. Divide by 6 on both sides, I get one of my critical values is 0 itself. Okay, square root both sides here. Square root of 0 is just 0, so no change there. We have x squared minus 1 equals 0. Add 1, add 1. I have x squared is equal to 1. Now, when we do this square root at the end, we do need the plus or minus because that does give us two critical values. Okay, we get critical value of plus and -1. So we have three critical values here. We have x equals 0, x equals +1, and x equals -1. We have -1, 0, and 1 as our three critical values. Let's draw a number line to visualize our test points that we need to pick. So now what we found is we have a critical value at -1, we have a critical value at 0, and we have a critical value at +1. We need to determine which ones are mins or maxes or which are neither. They're inflection points. So we need a test point in each one of these intervals. So we need 4 test points this time. I'll use -2. I'm going to have to use -0.5. I need a decimal, something between -1 and 0. Same thing over here, +0.5, a number, some number between 0 and 1. I'll just pick an easy 2 for that side. So our test points that we've chosen, or I've chosen, and again, it's just a choice. You can pick any number that's in the intervals. Doesn't matter what you choose. I try to keep it as simple as possible. So let's now plug these into our derivative to determine positive or negative outcomes. So recall our derivative is 6x times x squared minus 1 squared. So the derivative at our first test point is -2. Okay. So we're going to put -2 in for every x. Put that in. Okay, and let's calculate. So we have -12 times, we're squaring a negative, which gives us a +4. +4 minus 1 is 3. 3 squared is 9. So we have -12 times +9. Again, it doesn't matter what the number is. What we care is that it's negative. So we're saying that to the left of the critical value of -1, we have a decreasing function. So we are negative. Okay, so now let's check our critical value of, what's the next one? Oh, sorry, not our critical value, our test point of -0.5. That is a test point between our critical values of -1 and 0. So we're going to test -0.5. Doesn't look like a 5. There we go. So -0.5. Oh, and -0.5. Let's do our calculations. Okay, so +6 times a -0.5 is going to be -3. A -0.5 squared is going to be a +1/4, so +0.25 minus 1 is going to make it negative, but then it's going to be positive again because you're squaring it. So -0.25 minus 1 is a -0.75, but then you square that and it gives you a positive number. This is already negative, so negative times positive gives us a negative. So between -1 and 0, we found that it is still decreasing, which tells us something about the critical value of -1, which we'll discuss when we're done doing all these calculations. Let's do our next test point, which is +0.5, and see what's happening with our function. See if we're decreasing still or if we're changing to increase. So we're going to put +0.5 in here. Okay, and we're going to get 6 times a half, which is +3. A half squared is +1/4. And we're still minusing 1 and squaring it. So we still have a -0.75 squared, which is going to come out to something positive when you square a negative number. The 3 is positive, so positive times positive is going to give us positive. All right, so between 0 and +1, our two critical values, we have an increasing portion of the function. Okay, lastly, we need to check our last test point of +2. That is a number bigger than our last critical value of 1 to determine what's happening to the right of our critical value of 1. Let's find out. So let's put in our last test point of 2 and calculate. So we have +12 times 4 minus 1 squared. So we have +12 times +9, which is going to be positive. So after +1, we are positive, so we are still increasing. Let's take a look at what we just found. Okay, so we have our critical values. We have a critical value at -1, a critical value at 0, and a critical value at +1. Now we just found through our first derivative test that when we put the test point of -2 in, we got a negative response for the derivative. So the derivative at -2 was less than 0 or negative. So that indicates a decreasing line, okay? Because we had a negative. Now, when we tested a -1/2 as a test point, we still came out with a negative derivative indicating decreasing on the original function. We tested positive zero point 0.5 and got a positive derivative, so that it's an increasing function. And we tested positive 2, which also produced a positive derivative, indicating we're still increasing. So if I was to draw this function, I would see something like this. Okay, so what they're saying is happening, excuse me, is that we're decreasing, which makes -1 an inflection point. That says inflection, even though my handwriting is horrible. And here, my picture is horrible too, but there is an inflection point at +1. Okay, this is also an inflection point. Let's just abbreviate it IP. Okay, IP, inflection point. The only one that is a max or a min is the critical value of 0. So we see that we are decreasing to increase, which we can see that that makes this a min. When we take a look at what's happening with the end behaviors, we have behaviors are both going up, which makes this a global min. This is a global min, or called an absolute min, because it is the lowest number of the function. All right, jumping back to our PowerPoint, I think we are finished the last example. We did. So this is maxes and mins, finding maxes and mins of functions. So if we recap, the first thing that we'll do is we find the derivative of the function. You then set that derivative equal to 0 and solve for x. Those are all critical values, including mins, maxes, and inflection points. And you use the first derivative test to determine what the behavior is of the function to the left and to the right of each of the critical values to determine what type of critical value they are. Okay, I'll see you guys in my next video on 4.3, discussing graphing and shapes of curves.